These days, you'll find cameras just about everywhere. They're on our cars, in our houses, they're all over our phones. But what about robots? Getting robots to be able to see and understand the world the same way that we do with our eyes is one of the biggest areas of robotics research. And today we're going to look at the first half of that problem, the seeing. How do we get data from the world into a robot using a camera? By the end of this video, you're going to be able to use ROS to connect to either a virtual camera or a real camera and process image data coming from it. And just like the last tutorial on LiDARs, this is going to be split up into 4 different sections. First, we're going to do a really quick overview of how cameras and images work. Secondly, we're going to look at how cameras and images are integrated into ROS. Thirdly, we'll be using Gazebo to simulate a virtual camera and drive around a virtual robot. And then fourthly, we'll be connecting a Raspberry Pi to a real camera and getting image data from it. And you can use the chapter markers at the bottom of the video to jump to any section that you want. In this video, we'll be focusing on RGB cameras, that's regular color cameras, but in the next video, we'll be looking at depth cameras, which are even cooler. Make sure you subscribe so that you don't miss out on that. While it's really exciting to get a camera working in ROS for the first time, getting those images beamed back to your computer, and it's tempting to just rush ahead and start typing things up and wiring it all together, things are going to make a lot more sense if we step back first and quickly cover some theory. The stuff we're about to talk about, you could spend an entire series or even an entire uni degree talking about. So we're only going to be looking at the bare minimum bird's eye view right now. When we think about cameras and images, there's probably something that jumps into our heads straight away. We imagine a 2D array of colored pixels that vaguely represents what we see with our eyes. And that's what we'll be talking about for most of this video. But it's worth acknowledging that there's actually a huge variety of cameras out there. They vary in their sensor type, so you can get color, grayscale, thermal cameras, infrared cameras. They vary in their optics, so you get wide-angle lenses that can see heaps of things, or telephoto lenses that are really zoomed in on one thing. Or sometimes you get high frame rate cameras that can measure things that are moving really fast. Or depth cameras that can measure the depth to an object as well as its colors and stuff. There's all sorts of different types of cameras out there. And the things that we're talking about in this video are going to apply to all of them in some way or another. When a camera takes an image, it basically takes all the light that's just bouncing around in the world, it focuses it through a lens, through an aperture, and onto a sensor. And that data is then stored as a 2D array of measurements that are called pixels. Now, for a grayscale image, this is pretty straightforward. Each pixel just measures the intensity of the light that hits it. But for colored images, it gets a bit more complex. There are a few different methods that can be used, but the most common one is to split the information up into 3 different color channels, red, green, and blue. And by combining these 3 channels together, we can produce all sorts of different colors. So if all of them are at their maximum, then you're going to get white. If they're all at their minimum, you're going to get black. And for something in between, you've got every other color you can think of. Now, usually we store this with 8 bits, so that's 1 byte per color channel per pixel. So those 8 bits give us a range of 0 to 255 different values for each color. And by combining the 3 colors, that gives us millions and millions of different color combinations. And we usually store that as red, and then green, and then blue. But we should be aware that some software and some hardware does things a bit differently. For example, OpenCV stores it as blue, and then green, and then red. Or you might get a camera that has data that's 16 bits per pixel, that sort of thing. In general, the same principle applies. This format of 3 8-bit values per pixel is really easy for computers to work with. But unfortunately, it's not very space efficient. And this starts to become a problem with robotics because we've often got large images that we want to send over a network many, many times per second. And so to deal with this, we use something called compression. The simplest form of compression is just to resize the image, just shrink it down, throw away, 3 in every 4 pixels. And this works, you'll save space, but you end up with a picture that's really pixelated. The good news is there are smarter ways to do this. There are compression formats like PNG and JPEG that will do a smarter job of this. For example, say you've got a big black patch in your image, instead of storing 000,000 for every single pixel, maybe there's some way it can recognize that all of this section is the same color. PNG does this in a way that's lossless, so when you compress on the image on one end and decompress on the other, you'll get exactly the same pixels back out. JPEG does this in a way that is lossy. So when you decompress it, you're not getting exactly the same thing out. You'll have lost a little bit of information, but hopefully it'll be done in such a way that the information that's lost wasn't that important. Now, the process of compressing an image on one end and decompressing on the other does take a bit of CPU power, but it's often worth it for the amount of bandwidth that we save. When we're taking an image, there's a whole lot of different parameters that are going to contribute to what that final image looks like, but there's just one that I want to touch on now, and that's the focal length. The focal length is technically how far away the sensor inside the camera is away from its lens, but that's kind of meaningless unless you know the size of your sensor. Instead, it's often easier to talk about the horizontal field of view. That's the angle spanned from the left side of the image to the right side. Then, when we increase the focal length, we're decreasing the field of view. We're making that angle tighter. And that's just the same thing as zooming in. So you can see in the image that instead of all the trees, it can now only see just above the person. Often in robotics, we care about seeing as much as we can of the world around us, and so we use cameras that are zoomed out. They're a fairly wide angle field of view, or equivalently a short focal length. If you do ever need to perform the conversion between focal length and field of view, there's the equation up on the screen now. It's just some plain trigonometry. The last thing I want to touch on briefly in this section is coordinate systems. Typically when we're working with images, the X direction moves from left to right, and the Y direction moves from top to bottom. And according to our right hand rule, that makes the Z direction pointing into the page or away from the camera. Keep that in mind, it's going to come in handy in just a minute. Now that we've got a general understanding of how cameras and images work, let's see how they're integrated into ROS. So just like we saw in the last video with LiDAR, we're always going to start with a driver node for our camera. So this is a node that's going to talk to the camera hardware. It knows all about that camera. It can set the frame rate and the shutter speed and whatever else. It knows how to speak that camera's language, and it's going to take the data stream from that camera and publish it to a topic. Now the type that ROS provides for us for that topic is sensor messages image. And that way, as long as your driver node is designed to publish an image, and as long as your algorithms are designed to subscribe to an image, then you can chop and change. You can use whatever cameras you want, whatever algorithms you want, and everything should work together. And if for some reason your driver or your algorithm only wants to deal with compressed images, ROS provides another type that's sensor messages compressed image. And as you guessed it, it's just the same sort of thing as image, but it's storing compressed data like JPEG or PNG. ROS also provides a bunch of libraries and tools called image transport, and they handle all of the conversion from compressed to uncompressed. So say, for example, your camera hardware only deals with compressed images, or your algorithms only want uncompressed images. Using those libraries or those nodes can allow us to convert between them, and we'll see a little bit of that later. The unprocessed image topic that's being published directly by the driver node is usually going to be called something like image raw. Now here, RAW doesn't mean the same thing it does in photography, if you're familiar with that, the RAW format. In this case, it just means it's the unprocessed image. It might be distorted and that kind of thing. If you've got a compressed image, then we usually add /compressed to the end of the topic. So in this case, it would be /image raw /compressed. There's also another type that ROS provides for us, and that's the camera info type. And as you might guess, the camera info stores the information about the camera. Things like how it's calibrated, distortion coefficients, that sort of thing. This is the kind of information that some algorithms will need in order to be able to interpret the raw image data correctly. This topic is typically called camera_info, and that lives in the same namespace as image raw. So say your image was in /mycamera/image raw, then your camera info would be /mycamera/camera info. We're not going to talk about the camera info anymore for the rest of this tutorial. It's just good to know. Lastly, one of the most confusing aspects about working with cameras in ROS is the coordinate systems. Now we've seen in earlier tutorials that the standard kind of ROS coordinate system is to have X pointing forward, Y pointing to the left, and Z pointing up. But just a minute ago we saw that the standard when working with images is to have X right, Y down, and Z forward. How do we deal with this? Well, the answer is we do both. So whenever we're creating URDF with links, or we're creating a transform tree, that sort of thing, we always have two different frames. We usually call the one that's in the ROS coordinate system the camera link, or something like that. And then the one that's going to be in the vision frame, which is exactly the same as this frame, but just rotated differently, is the same name, but with _optical. So you might have camera link and camera link optical. Then all of our topics, so our image topics, our camera info topics, in their headers should specify the optical frame, not the regular frame. I know this is really confusing, but it's just how it is to deal with this problem. We're going to get to see a practical example of it in just a minute, as we're about to start simulating a virtual camera in Gazebo. Now, just like the last tutorial with the LiDAR, we're going to be simulating the camera first in Gazebo before we try and plug in a real one. And so if you do feel like I'm moving through things a little bit too quickly, then maybe check out that LiDAR tutorial first for some clarification. Now, because the camera is going to be so similar to the LiDAR, we're actually going to start by taking our LiDAR file from the last tutorial and we're going to copy and paste it, and we'll rename it camera.exacro. And then we'll go into our robot.uidf, copy and paste the line where we include the LiDAR and rename that to camera as well. So we'll go through this file now and we'll change a few things. So our first joint is now going to be called camera joint instead. And our first link we're going to call camera link. Oop. Then obviously this joint is now going to be between the chassis and the camera link. And for the location of this, I'm going to put it at the front center of my robot. Now my robot origin is at the back and it's 300mm long. So I'm going to make this 0.305 meters because it'll have a bit of thickness to it. So the origin of the camera is going to be sitting just in front of the chassis. And let's make it 0.08, so 80mm high from the bottom of the chassis. Now you'll also note that I haven't put any rotations in here, and that's because for now at least, this camera joint is going to be using the ROS standard of X being forward, Y being to the left, and Z being up, rather than the optical standard. We'll get into that in a minute. Now for the link, you've got the visual and collision and inertial components here from the LiDAR. Now you can keep all them if you want, but I'm actually going to get rid of the collision and inertial components. Because my camera is really small and it's just going to be affixed to the chassis, I'm going to get rid of those components and just have the visual. And I'm going to change that to be a box that is of size, let's go 10mm thick. So that accounts for twice that extra 5mm. Then we've got 30mm in each of the other dimensions. So this should give us a little square prism sitting on the front of our robot. I'll keep the material as red from the LiDAR. Now in our Gazebo tag here, we better change the Gazebo reference to the camera link. Now I'm going to comment out this sensor section for now. We're not going to worry about that just yet, and we'll leave the material there. So we've now got our camera exacro file. It's got a new joint and the camera link. The other thing we're going to do now is to add that special extra link and joint that convert from the ROS coordinate system to the general vision standard coordinate system. So I'm going to copy and paste the joint here. So I'm going to call this joint the camera optical joint. The parent link is going to be the camera link, and the child link is going to be called camera link optical. So normally this is going to be whatever your camera link was and then optical afterwards. Now the origin, you want the origin to be located at the same point as your camera link, but it's going to be rotated differently. So we want it to be roll minus pi on 2, no pitch, and then yaw is also minus pi on 2. And we'll see soon that that's just what it has to be to make it work. For the actual link itself, we'll just get rid of all of these components. It doesn't need to have any sort of visual or collision or inertial associated with it. It'll just be that camera link optical. It's kind of an invisible joint that just gives us an alternative way of looking at our camera link. Now you notice that I actually put this in between the camera link and the Gazebo tag. Normally I like to keep my Gazebo information close to the links there, but because this one is kind of just another way of looking at the same link, sort of an alias for it, I'm happy enough to keep it nice and close to here rather than putting it at the bottom of the file or something else like that. Okay, so we've got camera joint, camera link, optical joint, and optical link, and then our Gazebo tag, which at the moment just has the material associated with it. So let's test that it works so far. I'll open up a new terminal. We'll get into our development workspace. We'll make sure we rebuild because we added some new files. And now I'll source my installation. And then you remember from the past we had our launch sim. So we'll go launch sim. So this is just like in the previous tutorial. It'll launch it up. We've still got our LiDAR there. But now, if we spin around, we should see our nice little camera sitting out the front of our robot. So that's the physical aspect of the link. Now we need to set up that sensor tag, just like we did with the LiDAR. So we'll close this, and let's see what we've got here. So I'll uncomment that sensor tag, and I'll just collapse some of these things up for now. So we're going to start by calling it, we'll call it camera, and the sensor type this time is going to be a camera sensor. Again, pose, put that as all zeros, it doesn't really matter. Visualize true, update rate 10. This ray section here, we're going to get rid of that because you remember those were the settings for the ray sensor, but this is a camera sensor now. So we're going to add a camera section. So the settings that are going to go in here, I've actually already copied from somewhere else, so I'm just going to paste them. Whoop. And let's take a look at those, and you can type them out as I go through them. So first up, we've got the horizontal field of view. This essentially determines how zoomed in or zoomed out the picture is going to be. I've chosen this number because it's pretty similar to the value for the actual camera that I'll be using. Now the image format. We've got our image is R8, G8, B8. So that's 8 bits of red, 8 bits of green, 8 bits of blue. And for the width and height, I've got 640 by 480 pixels. You can kind of change that to be whatever you want it to be. And then finally, I've got some clipping settings. So this sort of sets a minimum and a maximum range that the camera is going to be able to see. So I've got mine set up so that it'll see as close as 50 millimeters and as far away as 8 meters. So that's all our camera settings. Now it's time for the plugin settings. So we've got the name here, laser controller. Let's change that to camera controller. And the file name here is going to be libgazebo ROS, and instead of a ray sensor, this time, it's libgazebo ROS camera. Now we'll get rid of these arguments. We don't need them for the camera sensor. And then for this one, the frame name, this is where it gets a bit confusing. Even though this is attached to the camera link, we actually need the frame associated with it to be camera link optical. So when it publishes the image data is going to be associated with this optical link, but the link that Gazebo is using for its simulations is the camera link. Very confusing, I know. It trips a lot of people up and you end up with cameras pointing the wrong way, but that's the way you got to do it because Gazebo is using one standard, the kind of ROS standard of X forward, whereas other nodes are going to be expecting to use the kind of image standard, which is to have Z forward and X to the right and Y down. So we got those settings all set up. So let's minimize that and we'll try rerunning Gazebo. Oh, and I've just realized we've still got our laser visualized here. So let's open up our LiDAR and we're just going to set visualize to false. It was good in the last tutorial while we were testing our laser and developing it, but we're happy that it works now. So we can disable it from being visualized. It'll still be running it. It'll still be publishing the LiDAR data to the scan topic. All right, so now we can see we've got our robot. We can actually see this little visualization of the camera. So we can see, even though it's kind of looking through it, we can see that it's seeing this little bollard thing. And so what I'll do now is open up the teleoperation. And so you should be able to see, as I drive this around, we can see our little robot is, seeing the different things. Now, what should happen is if I get too far away, once we're more than 8 meters away from a particular object, we should start seeing it disappear. So you can see these rearmost cones are starting to fade out of the field of view. Once we get 8 meters away from these bollards, they'll start to disappear as well. So that's kind of showing that maximum clipping distance that we can set. So what about in RViz? Let's open up a new terminal here. We'll start up RViz, fixed frame to ODOM. Now this time we'll add an image topic, an image display I mean, and in the drop down here we should be able to see we've got camera, camera info, and camera image raw. And if we select that, now we're not seeing anything there now because we drove our thing too far away. So I'm just going to drive it back toward the thing. And so we should see these start to come into view here. Now, what we can also do is we could add a camera display. Now, the camera display is very similar to the image display. So again, we can select the topic and we'll select camera image raw. And this looks the same, but you might be able to just see there's a bit of a grid here. And what this does is it uses the camera info to figure out where this image sits within the world. And so if we had other robots driving around, or obstacles we detected, or maybe a grid map that we'd laid out, we'd be able to see this camera image overlaid on top of the other contents of the scene. As it is, all we've got right now is the background grid. So we can kind of see that the horizon of the grid there lines up with the horizon in our image. So that's good. That means we haven't got our image kind of pointed in some weird direction. Now, you'll notice when we did our drop down here, we had these options of camera image raw and camera info. And there's no option for a compressed image. And that's because at the moment, we actually haven't got the plugins installed for image compression. So we're going to close these down. So I'm going to open up a new tab here and type sudo apt install ROS Foxy image transport plugins. Enter the password. So it's going to install the compressed image transport as well as a couple of other things. And now that that's installed, we can go back to our Gazebo window here. I'm just going to source the installation again, just in case it's not found it. It should be all right. And now I'm going to rerun our Gazebo simulator. And while that's starting up, I'm also going to rerun RViz. Swap that to ODOM. Add our image display again. And what we should find now, is we've now got the options for image raw like we had before, but we've also got compressed, compressed depth, and Theora. So if we go to compressed, we might expect to see this, but it says no image. What's up with that? RViz can't actually handle compressed images. It's a bit annoying. So instead what we're going to do is we're going to install another piece of software. Actually, I'll use this window again, and we'll go sudo apt install ROS Foxy RQT image view. And what image view does is it will let us view both compressed and uncompressed topics. So we can now type ROS2 run RQT image view. It'll pop up this little window and we can see our topics here. So sure enough, we've got that image raw, but we can also view the compressed topic. Drive it around, we can see that that topic is being updated as we drive our robot. So that's great. We've now got the Gazebo simulator that's publishing compressed and uncompressed images from a simulated camera. But sometimes when you're using a real camera driver, if they haven't written the driver properly, you might only get a compressed image or only get an uncompressed image. So before we move on to working on a real camera, I'm just going to show you how to create a compressed or an uncompressed topic if you're missing the other one. So what I'm going to do is I'm going to open up a new tab here and I type ROS2 run image transport list transport. And this is going to tell me all of the different types of image formats that our system knows about right now. So we've got compressed, compressed depth, raw, and Theora. So they're those ones that we saw. So to take a topic that's got an image of one type and republish it to an image of another type, we can type ROS2 run image transport, and we'll use the republish node. Now we need to say what the format of the input is and then the format of the output. So in this case, let's say we've got our input is compressed, but we want to output as raw. And we now need to specify what the topics were. So we go ROS args, this is done as a remap. So we're going to remap the compressed input topic. So we go in compressed, and we can remember from up here that that's /camera /image raw /compressed. And we want to map the raw output topic, so out, as /camera /image raw. Now that straight camera image raw is already taken, so let's go uncompressed. We'll just call it that. So now this is running, and so we can refresh this list of topics here, and we should now see we've got /camera /image raw uncompressed. Sure enough, that's working. And if we go back to here and drive it around, that's updating it. So that's taking the compressed image that was being published by Gazebo and then uncompressing it to this new topic. And this can be helpful if you want to compress data, send it over the network, and then uncompress it on the other end, that kind of thing. So now that it's all working in Gazebo, we can have a go at connecting to a real camera. So we'll start by plugging in our camera. The camera I'm going to be using is the Raspberry Pi Camera V2, and that just connects by connecting this little ribbon cable to these clips. So you just lift up the little black thing, put the cable in, put the clip back down, make sure you do that on both ends. And here's some pictures of what it looks like on each end, so that if you're having any trouble, you can pause that and check it out. I've also there got a little 3D printed mount that I made for my one on the prototype. I'll include a link to that in the description, but I'll be redoing that for the new build, so you don't need to worry too much about that. All right, now before we start, there's a few pieces of software I've got to install. I've connected to the Raspberry Pi with a monitor just because I find it a bit easier for getting the camera set up, but you can do all this over SSH if you want. So we'll install lib raspberry pi bin, v4l utils, and ROS Foxy v4l2 camera. v4l is just video for Linux. It's like a common video driver library thing. So once that's installed, we also want to make sure we're in the video group. So we type groups, and I can see there my user is in the video group. But if you're not, then the command that you run is sudo usermod-a capital G, and then the group, so video, and then your username. And then once you run that, you want to log out or reboot. But I don't need to do that because I'm already in the video group. So the Raspberry Pi comes with a command that we can run to check if the camera's connected. So we type vcgen-cmd get_camera, and it'll tell us now it's supported and detected, so that's good, camera's connected. Now we can type raspi-still-k to stream the data from the camera, and sure enough, there it is, the camera is seeing this little coordinate marker I've got next to my wall. And to quit this, you just type X and then enter. So now that the camera is working, we want to see if the video for Linux kind of subsystem can see it. So we'll type v4l2-ctl and then --list-devices. And you can see there /dev/video0 at the bottom. That's the one we want. So it's connected there. Now there's a few other things we've got to quickly install that I forgot to do before. So we want to install the image transport plugins and also RQT image view. We already saw how to install them in the simulator one. So we're just doing this on the Pi now. So we'll just speed through that nice and quick. All right, so now we can run the video for Linux node driver. So we'll type ROS2 run v4l2 camera, that's the package. And then v4l2_camera_node is the node name. And it's got a couple of arguments. The first argument is going to be the image size. And I'm going to set that to 640 by 480. You just specify that as an array in quotes. And then we also want to set the transform frame that our camera is going to be in. So that's camera frame ID. And you remember from before, we're going to set ours to camera link optical. So hit enter. That'll start up the driver node. And it'll start spewing a bunch of errors. You don't need to worry too much about these. Most of them are going to be telling us about things on the camera that it can't control, and that's fine. I'm not too worried about controlling those things. And then it's also telling us that it hasn't got a calibration file, but I'm also not too worried about that. If those are a problem for you, then you might need to find a different driver. So we can start up RQT image view. And then we'll see there we've got our image topics, including the compressed ones. So I'm going to select image raw compressed just for the sake of it. And now I'll go reach over and pick it up so that you can see that it is in fact streaming the image data on that topic. So that should all be working now. You should also be able to connect to another computer on the network and see the images streamed over the network. It is worth noting that, at least in the current version, that V4L2 camera node can't control the frame rate of the video. It looks like that is an update that they're planning on pushing out, so hopefully that'll be in soon. I haven't actually tested it, but it'll be good once that's in so that you can restrict how fast the frames are coming out, because sometimes if they're coming too fast, it can bog down your network a bit. So now I'm just gonna also show that we can run this in a launch file, just like we did with the LiDAR. So I'll show you the context of my camera.launch.py. I've just got it in my home directory at the moment, but I'll put it in the repo that everything else is in and include a link in the description. So just like with the LiDAR one, I can just type ROS2 launch camera.launch.py, although normally it would be in your package. So that's running now. That's all that same text, it's just not colored anymore. And once again, we can run the image view, and sure enough, there it is, working just like it was before. So there you have it. We've got a bit of a handle on all things cameras and images in ROS. We can connect to a virtual camera or even a real camera, and this opens up a huge array of options. So we can start doing things like driving a robot around and getting visual feedback on a screen, or we can start having a robot track an object with its camera and follow it around. Those are both things that we're going to be covering in future tutorials. Make sure you subscribe so that you get to do them when we get to it. But before we get to that, in the next tutorial, I'm going to be showing you how to set up a depth camera. And a depth camera not only sees the world around it, but it sees how far away it is. It's kind of like a cross between a camera and a LiDAR, and I'm really excited to set that one up. If you do have any other questions, let us know in the comments. Otherwise, as always, I'll see you next time.